In this video, we will try to derive a formula for the equation of a plane. So I want to begin by making the following observation. So a plane is determined by three non-collinear points. So let's call them P0, P1, and P2. So non-collinear means they are not all on the same line. So they're not all on the same line. Okay, so let's look at an example picture. So let's say that I have some points, P0, and let's say P0 is 1, 2, 3. And I have another point, P1, and P1 is negative 2, 4, 3. And then I have a point P2. Let's say that P2 is 5, 1, 4. All right, so I'm just going to scooch this a little bit down so I have a little bit more room to draw. Okay, so those 3 points, they will make up a plane. So I'm just going to draw a plane that contains those 3 points. So let's just say that my plane looks something like this. Okay, so I have a plane that has these 3 points on it. So if we know these 3 points, how do we get the equation of this plane? How do we get some more information about the plane? So we can use those 3 points to get 2 vectors on the plane. So there's a few different ways we could do this depending on how I draw my vectors. So if I draw one vector starting at P0 and going to P1, I can form a vector. So let's just say I call this vector U. So if I write down the components of U, I would have negative 2 minus 1 for the first component, so that's negative 3. 4 minus 2 for the j component, and then 3 minus 3, which is 0, for the k component. All right, so that's that vector, negative 3, 2, 0. I could get another vector by drawing from P0 to P2. So I get a vector. Let's call this vector V. And if I do the same thing to get its coordinates, I would have 4, negative 1, 1. All right, so that is the vector V. So now that we have these 2 vectors that are on the plane, what are we going to do to get a normal vector, which I'll call n? So I'm going to try to get a perpendicular vector to the plane, because that's what a normal vector is. So we will take, let's keep this in black actually, we will take their cross product, to get n, the normal vector. Okay, so for example, the normal vector, once I cross these two, once I do U crossed with V, we'll work out what that is in a sec, but let me draw it. So when we do U crossed with V, using the right-hand rule, so U crossed with V, our thumb will stick up, straight up. So make sure you see Y. Make sure you see Y, because this is the hardest part. That's the hardest part to explain in a video like this. But please refer to the video that I posted about the right-hand rule, back when we talked about cross products. So okay, so that is U crossed V. Now I'm going to let that be n, my normal vector. Okay, so to compute that normal vector, we'll take a determinant. So we would get I, j, k. We always put that at the top. And then we put whatever the first vector is in the cross product, which is U, on the next row. So negative 3, 2, 0. And the second vector, which is V, on the bottom row. So 4, negative 1, 1. And evaluating this determinant, we end up getting I hat times 2 minus 0. And then in front of the j hat, we always put a negative sign. So negative j hat. And j hat is going to get multiplied by negative 3 minus 0. If you're unsure where I'm getting these numbers from or how I'm evaluating this, refer to our video on the cross product again. I talk about how to use this thing called the determinant to get this cross product. Okay, and then we put a plus in front of the k hat, and k hat will be multiplied by, so negative 3 times negative 1 is positive 3, and then minus 2 times 4 is 8. And if we simplify that, that is 2i hat plus 3j hat, and then minus 5k hat. That is our normal vector. So why is having the normal vector useful in terms of getting the equation of the plane? That's what I want to talk about next. So to answer this, I'm going to begin by drawing a general picture. So in the general picture, let's just say that I have my plane here. And in the plane, I'm going to draw some point that I know. I'm going to call it P0, and I'll call its coordinates x0, y0, z0. And then I'll write down some other point on the plane. Let's call it P, but this one I'll keep it arbitrary. So its coordinates I'll call x, y, and z, which are going to be variables. So if I draw a vector connecting the two, P0 to P, we get the vector P0, P, that's how I notate it, and it is x minus x0, comma, y minus y0, comma, z minus z0. So that's that vector P0, comma, P. And now let me also draw a normal vector to the plane. So let's say that this is a normal vector. So the normal vector is going to be orthogonal to the plane. Now let's just write that the coordinates of the normal vector are a, comma, b, comma, c, once I put it in this component form. So one thing that's always going to be true is the normal vector dotted with any vector of the form P0, P. So any vector like P0, P is going to be 0 because the normal vector is orthogonal or perpendicular to every single vector in the plane that I could draw like this. That's why their dot product is 0. Okay, so I meant for this to be kind of like a big bullet point. I'm trying to make it larger so I don't confuse it with just the dot product dot. Okay, so those are all bullet points. I think I have one more up here. Yeah, this is also a bullet point. All right, so now this is true for any point P in the plane. So let's compute this dot product in our example. So our normal vector in the example was 2, 3, negative 5 if I put it in component form. And if we dot this with the vector P0, P, so let's look at what P0, P looks like. It's x minus the x coordinate of a known point. So I could technically use any of these 3 points because I have 3 points on my plane. Let me just use the point that I called P0. So I'll do minus its x coordinate, which is 1, and the next component is y minus the y coordinate of that point, which is 2, and then comma z minus the z coordinate of that point, which is 3. So that needs to be equal to 0. And now if we dot this, we get 2 multiplies x minus 1 plus 3 multiplies y minus 2. And then we'd get minus, because it's negative 5, minus 5 times z minus 3 equals 0. And that's the equation of our plane, but I can simplify it a little bit. If we distribute, we get 2x minus 2 plus 3y minus 6 minus 5z plus 15 equals 0. And it's convention to keep all the terms with an x, a y, and a z. So the x, the y, and the z on one side. So we get 2x plus 3y minus 5z. And then to move the constant terms to the other side. So 15 minus 6 minus 2, that's 7. And if I move it to the other side, we get negative 7. And that is the equation of our plane. So really the key things that we needed to know to get the equation of the plane were, we needed the normal vector, so we needed this n, and then we needed a point on the plane. We needed the P0. From there, we could take this dot product, n dotted with the P0, P vector, set it equal to 0, and then just multiply stuff out to get the equation. So what's the general formula? The general formula just mirrors what we just got right here. So in general, the equation of a plane that contains the point x naught, comma y naught, comma z naught, and has a normal vector n, which is a, comma b, comma c, once I put it in this component form. So notice how we write a point. A point we put with the parentheses, versus a vector we put with these sharp brackets. And that's why I distinguish between the two. So in general, it's going to be, you take the normal vector and you dot it with the vector x minus x naught, comma y minus y naught, comma z minus z naught, and you set that equal to 0. And that's equivalent to, once you write what n is, it's equivalent to a, comma b, comma c, because that's the normal vector, dotted with x minus x naught, comma y minus y naught, comma z minus z naught, and that needs to be equal to 0. All right, so I'm going to highlight these. So this is how I can set up the equation of a plane if I know the normal vector, which is n, and one point on the plane, x naught, y naught, z naught. All right, so when we take that dot product and when we multiply everything out, we get that a plane's equation can always be written in the form ax plus by plus cz equals d for some so a, b, c, and d in this equation are just real numbers. That's what this notation means. It's saying that they are elements, that's what this E symbol means, elements of the reals. Where the vector, where you take the a, the b, and the c, and write them as the the components of that vector, is a normal vector, to the plane. So as we'll see in the next video, if we have the equation of a plane, and I can just see what the a, the b, and the c are, I just put those into a vector, and that happens to be the normal vector. That's what we just showed in our derivation in this video. All right, so in terms of our goals for this section, we have derived an equation of a plane using vectors. In the next video, we'll do an example where we find the intersection of two planes.